Okay. All righty then. Okay, so let's see if I could get this going again. Here we go. Let's see. Okay, we see PowerPoint, right?
Yes.
All righty then. Okay, so let's get started. So back in class, we solved equations, and the equations that we solved had real solutions. So to understand what a real solution is, we need to look at the number line. So this is my best way of showing a number line. And the number line has an infinite number of numbers. It's just way too many numbers. It has integers. So for example, these kind of numbers. Okay. And it goes out to infinity. So it's a really, really long number line. But also it includes some other numbers. For example, like here, we could say, I don't know, what would be 3/2. 3/2, which is the same thing as 1.5. So real numbers or solutions, as we were trying to do. So real numbers include whole numbers, it includes positive, it includes negatives, it includes also fractions. So for example, if I write any fraction that if I write 11/7, that will be a real number. But it also includes some other numbers that look a little funky, like pi. Okay. Now pi is a real number, but it cannot be represented as a fraction, but it's a real number. Another real number that looks a little funky is the number e. Okay. So this is approximately, we say 3.14. This is approximately 2.718. Okay. But other numbers that are also real include the square root of 2. Okay. So there's a whole bunch of numbers that are real. Okay, where are we going with this? Well, there is a whole bunch of numbers that are not real. And these are called complex numbers. So we have real numbers and we also have complex numbers. And if I were to define a complex number in a very short way, well, a real number is not real. It is imaginary. So you're probably wondering, where is this coming from? Well, the birth of complex numbers is from trying to understand the idea of the square root of -1. So let me try to do my best to try to show you why this quantity here is imaginary. The square root of 4. I don't know what's going on with the computer with it, but it's acting kind of funky. Okay. The square root of 4 is equal to 2. The square root of 9 is equal to 3. But also the square root of 4 is -2. And also the square root of 9 is -3. Why is that? Because if we square these quantities, the answer will be 4. If we square these quantities, the answer will be 9. Positive times a positive will be a positive. Negative times a negative will be a positive. So what is the square root of -1? That means that there has to be a quantity that when it is squared, that is multiplied by itself 2 times, it has to be negative. But that cannot happen because I just showed you a little while ago that positive times a positive will be positive, or negative times a negative is positive. So there is no way that I can square such quantity and that be negative. It's just not going to happen. So what what mathematicians did back in the day is they said, you know what? We need to create something new. and they said that this is the imaginary unit. This right here is the birth of complex numbers, is the birth of imaginary numbers. Okay, so the square root of -1 is I, and I stands for the imaginary unit. Okay, so then we can have a whole bunch of numbers that are now imaginary. For example, the square root of -4. So how would you do this? How would I do this? The moment I see a negative inside of a square root, this negative inside here comes out, and it comes out as the imaginary unit. And then we do the square root of 4. Well, what is the square root of 4? The square root of 4 is 2, so I'm going to write this as 2 times I, where I represents the fact that this must be an imaginary number. Let me give you another example. The square root of -9. Oh, I see the negative inside the square root, so this has to come out as the letter I. And then it's just the square root of 9. The square root of 9 is 3, so we have 3I. Okay? All right. Any questions with this so far? We good? Again, you can use the chat or you could just say yes, but I'm going to assume that there's a long period of silence, is that we kind of get what I'm trying to say. Alrighty then, so I'm going to move on to another slide here, and I'm going to call this slide complex numbers. On the previous slide, I kind of show you where they're coming from, but I need to be a little bit more technical. A complex number is made up of two parts. It's made up of a real part and is made up of an imaginary part. So every complex number has a real part and it also has an imaginary part. So let me give you some simple examples. 5 plus 2i. That will be a complex number. Where in this case, the number 5 is very real, but 2i is imaginary. Let me give you another example. 1/2 plus, I don't know, 3/5 I. 1/2 is very real, but 3/5I is the imaginary. I could also do something a little bit more complex, and I could say something like this. Pi minus I. Well, I said earlier that this is very real, but this would be imaginary. So these three examples are examples of complex numbers. Okay, we could even have something. I don't want you to think that it cannot be negative. So negative 17 minus 14i. There we go. Where this is the real part. That's the real part, and this is the imaginary part. Okay, so every complex number is made up of a real and imaginary part. So what can we do with imaginary numbers? What can we do with, what can we do with complex numbers? We can add and we can also subtract. Just like we do with real numbers. You know how to add and you know how to subtract. So let me add, two complex numbers. I'm going to try to keep them simple. So I'm going to add 5 plus 2i plus, let's say, 6 minus 4i. So how would I do this? Well, because I'm doing an addition, I really don't need this parentheses. So I'm just going to do plus 6 minus 4i. Let me go ahead and get this out of the way there so it doesn't get in the way. Okay. And then what would I do? I will combine like terms. I'm going to combine the 5 and the 6 because they're real. So that makes it 11. And then I'm going to combine the imaginary parts in a, in a positive 2i with a minus 4i. That will be minus 2i. So there it is. That's how I would add complex numbers. Let me do a subtraction, and I'm going to use the same complex numbers. 5 plus 2i minus 6 minus 4i. Now I'm going to be a little bit more careful. On the first complex numbers, I can go ahead and get rid of the parentheses. But here, this negative will distribute into both of these numbers. So therefore, when I get rid of the parentheses, we'll get minus 6, and we'll get negative times a negative becomes positive 4i. So I just need to pay a little bit more careful or pay a little bit more attention to when I'm doing a subtraction because of this, okay, because of this. All right, so then combining like terms, this will be the reals, which will give us -1, and the imaginaries will give us plus 6i. Questions on this? So quite frankly, when we're adding or subtracting complex numbers, sometimes I think of it as just combining like terms. You just have to be careful with the subtraction because, as you saw here, the negative will distribute into both of these numbers. So make sure you're paying close attention to something like that. With addition, there's really nothing, yes, you still want to be careful. Make sure that you combine the like terms, but hopefully it doesn't trip you up. All right, so now, okay, we added, we subtracted. Now let's do some multiplying complex numbers. Okay, so multiplying. If it doesn't have a parentheses, we don't have to distribute, right? Correct, correct. But let me show you. We're not going to find something like this though, okay? So when they're asking us to subtract, it's going to be in this form. Okay, let me just rewrite this again. 5 plus 2i, and then you're going to see it minus, and then in parentheses for the other complex number. Okay, so it will not be, let me use a different color now. I've yet to see it like this. I have yet to see it like this. I've yet to see it like that, okay? Because we want to say that the reason why we won't see it like so is because we need to tell the audience that this is one complex number and this is the other complex number. Does that make sense or no? Okay, awesome. All right, let me go ahead and erase this. All right, and let me make sure I click. Okay, so what are we doing? We're multiplying complex numbers. All righty then. So in order to be able to do this, we need to be really, really comfortable with distribution. So I'm going to show you something real quick. So I'm going to multiply 5 plus 2i, and I'm going to keep it simple. And I'm going to multiply it with 1 plus 2i. I'm going to try to keep it as simple as I could possibly can. Okay. Now, the method that I'm going to use for multiplying these complex numbers is the foiling method. Okay. All right. Which is basically two distributions going on at the same time. So this is what it looks like. Okay. This is what it looks like. 5 is going to multiply the 1. That's referred to as the first term. Okay. Then we're going to multiply the outer terms, which will be 5 times 2i. And then we multiply the inner terms, which in this case will be 2i times 1. And then that will be the inner part. And then the last part is considered 2i times 2i. Okay, let me try to see if I can do that better. Okay, I am multiplying 5 plus 2i times 1 plus 2i. And I'm using the foiling method for multiplication, which is 5 times 1 will be the first terms, because they're the first term here, and this is also the first term here, so they're considered the first term. Then I'm going to do the outers, which in this case will be 5 times 2i. Well, that will be the outer terms. Okay. Then we're going to multiply the inner terms. Inner. And then we'll multiply the last terms, which in this case will be 2i times 2i. Okay. Alrighty then. So that will be the last term. Okay. Alrighty then. So let's go ahead and get going. 5 times 1 is just 5. 5 times 2 is 10. But that's 10i. Then we do 2i times 1, which is 2i. And then we'll do 2i times 2i, which will be 2 times 2 will be 4. And then I times I is I squared. Okay. I times I is equal to I squared. Okay, so, but there's something about I squared that is very important to know. I squared, by definition, is the number -1. So every time we see I squared, it will get changed to -1. So right here, this number I squared becomes -1. So let's see what that looks like. We have 5 plus 10 and another 2 makes 12 i's. This 4, that 4i squared becomes 4 times -1, which is just -4. So basically, to give you a little hint, I squared changes the sign of whatever number is in front of it. So here we had 4i squared. So the I squared changes the sign of the number in front of it. So it just becomes -4. And hopefully that helps you. So 5 minus 4 is 1. Excuse me. So that multiplication is 1 plus 12i. Okay. All right, I'm going to do another multiplication because one example is not enough. Okay, so I'm going to do another multiplication. So I am going to do, let's say, 3 minus 4i. And I'm going to multiply with, I don't know, -2 minus 3i. Okay. I am not going to forget that I squared is equal to -1, or that I squared changes the sign. I'm just going to leave it, I'm going to leave it like that. It's just that it changes the sign. I'll deal with this once I get there. So we're going to use the FOIL method to multiply this out. Meaning we're going to multiply the first terms together. 3 times -2 will be -6. Then we multiply the outer terms. That will be the outer terms. 3 times -3 is -9, but don't forget the I. Then we do the inner terms. That will be this ones. Okay. -4 times -2, that's +8. Don't forget the I. And then we do the last terms, which would be this ones. And that will be -4 times -3 is +12. And then we have I times I, which is I square. But the I square changes the sign of the number in front of it. So instead of that being a +12, that is -12. So now we could do combining like terms. We can combine this -6 with the -12. That becomes -18. Then we combine -9i with the +8i, and we get -1i. There it is. And I hope that the second example was a little better than the first example, since we kind of knew what kind of stuff we were getting ourselves into. How are we doing so far? I'm going to leave that there. Maybe you need a chance to copy it.
So we can multiply real numbers with imaginary numbers, but not add them, right?
That's right. So yeah, that's a great question or great comment. We could do 3 times 4i. That is 12i. But what we cannot do is 3 plus 4i. We cannot say that that's 7i. That is not true.
Okay.
Okay. Yeah, you're very right about that. That was a great observation. Great observation. All right. So for those of you that just kind of came a little late, where did this I come from? Okay. Where it comes from is the fact that the square root of -1, it's impossible to get this. So what mathematicians did is they said that we're going to call this the imaginary unit, and we use just I for the imaginary unit. So any number that looks like so, for example, for I, this is an imaginary number. Or numbers that look like 3 minus 4i is also, well, I'm going to call it more like complex, right? It's a complex number. This is also a complex number. And every complex number has a real part and an imaginary part. Okay. So not that I want to get too involved in this, but 0 plus 4i, this will be the real part. But this kind of funky to write it like so we just write just 4i. But 4i is a complex number where the real part is 0. Okay. Okay. And in the case of 3 minus 4i, very complex. 3 is the real part, while -4i will be the imaginary part. Okay. Are we okay with that? Yes or no? Yes, okay, thank you, sounds good. So far, do we need another example on multiplying or maybe adding complex numbers, subtracting? Because if not, then I'm going to do division, okay? Alrighty then, I think I'm going to jump into some division and see and see what it looks like with complex numbers. All right, so alrighty then. All right, so let's do some dividing complex numbers. So let's do some dividing complex numbers. Okay. And so let's try to do a simple example. Let's do, I don't know, let's do 3 plus 2i divided by 1 minus I. Okay. But before I jump into how to do, how does this look like? Let me give you a little bit of background. Recall that a complex number is of the form a plus bi. But every complex number has like a brother, and it's called a conjugate. And the conjugate looks like so. A minus bi. Notice that the real part stays exactly the same, but is the imaginary part that changes sign. So for example, if I have 1 minus I, its conjugate will be 1 plus I. If I have a complex number that looks like 5 plus 2, or let me do it like this, negative 5 plus 2i, its conjugate will be negative 5 minus 2i. Okay. If a complex number looks like I, okay, that will be like 0 plus I. Its conjugate will be 0 minus I. Okay. Alrighty then. Why am I saying this? I am saying this because back in the day, we decided that in order to do this, we're going to multiply top and bottom by the conjugate of the denominator. This is the denominator. So what we're going to do is we're going to multiply the top and the bottom by the conjugate of the denominator. So that will be 1 plus I, 1 plus I. All right, so what does this look like? Well, let's first do the numerator. We have the first term, so 3 times 1 is 3. Then I'm going to multiply the outer terms. 3 times I will give us 3 i's. And then we'll multiply 2i times 1, which is 2 i's. And then we'll do 2i times I, which is 2i squared. What does the I squared do? Can somebody please refresh me on what does the I squared do?
Doesn't it change the sign? It
It
makes different
changes the
units.
sign. That's right, that's right. So instead of being a +2, this just becomes a -2. So what we have here is 3 minus 2, which is 1. And then these two together becomes 5i. And then I got to multiply the bottom. Okay, that was just the top. Then I got to multiply the bottom. Okay, here we go. Multiplying the bottom. 1 times 1 is 1. 1 times I is 1i. Now this will be the inners. So negative I times 1 will be negative I. And then here we go. Be careful with your signs. That becomes negative times a positive will be negative I times I is I squared. But what does this become? Given that this is a negative 1 right here, negative 1, what does this number become?
Would that be a positive one?
That's right. It becomes positive 1. You're right. What happened with these two terms? What do you think happens with these two terms?
They cancel
They
each other?
cancel each other out. So what is 1 plus 1? That will be 2. Okay. So the final answer should be written in this way. 1 over 2 plus 5 over 2i. And the reason we do that is because that way we know exactly what the real part is, and we know exactly what the imaginary part will be. Okay, so we call this in standard form. We always write our complex numbers in standard form. Okay, so we separate it so that we know what is the real part that is separate from the imaginary part. How do you feel about dividing? Honest opinions.
I feel like it's more easier.
It's a whole lot of being able to multiply complex numbers, right? There was never any division going on here. It was just being able to multiply. So let's do one more example, and then we'll see what we could, let's do one that is relatively simple. Let's not make it too complicated. Let's do negative 5 plus 3i and divided by negative I. We'll do that. So let's see. Well, this number, negative I, has a real part, and that real part is 0. So its conjugate will be 0 because we got to keep the real part the way it is. But this becomes now plus I. Does that make sense? Yes or no? So what we're doing is we're multiplying the top and the bottom by I. That's the way to do this, okay? That's the proper way to do this type of examples. So this is going to be slightly easier than the previous example because we have distribution. That will be negative 5i. Here we have positive 3i squared, but I'm going to circle this because something is going to change. That positive 3 becomes negative 3 because of the I square. So that is negative 3 minus 5i. In the denominator, we have negative I square. But the I square changes the sign, and that becomes 1. So the final answer here is negative 3 divided by 1 minus 5 over 1i, or just simply negative 3 minus 5i. Questions about this example? Oh, excuse me. Oh. No questions?
Are we gonna have any
you.
examples where, where we can divide like the numerator by the denominator? Like if
Uh,
we have like,
yes, I would just have to think really, really hard on, what are those examples, but I can probably just write one up. Like, for example, at the very end, we have something that looks like this, negative 6 plus 18i and divided, let's say, for example, I'm going to say we get a 4 at the bottom. Let's say we get a 4 at the bottom. Okay. And so then in that case, we'll do negative 6 over 4 plus 18 over 4i. But then we have to recognize that this fraction can be reduced to negative 3 over 2. And this fraction can be reduced to 9 over 2i. Is that what you were talking about?
yes,
Okay, yes, absolutely. I just have to think really, really hard on like the example that will be like that. But if it comes out to something like this, don't forget to split it into the real part and then the imaginary part, and then simplify your fractions as needed. Okay. Yeah, so yes, that can definitely happen. That can definitely happen. Okay. All right, then what else on multiplying complex numbers or dividing complex numbers? Nothing? Okay, then. I am going to try to do the next thing, which is going to involve something called factoring. Okay. And so the idea, based on what I saw on the Alex topics, is that we have things that look like so. Ax squared plus bx plus c. Okay. And the idea is that we would like to take something that looks like that and write it into something that looks like this. X plus, I don't know, a number. I'm going to use maybe something like, I'm just going to do this, a number, and then, for example, X plus another number, because I didn't want to use A and B because I don't want you to think that it's the same numbers here. So the idea is that we're taking something that looks very much like a sum of terms, and we are writing a multiplication of things. Okay. So let me start simple. Let's say we have something that looks like x squared plus 2x plus 1. Okay. The way we want to do this type of examples, the example that you have in front of you, okay, is like so. This is the way I do it, okay? What numbers multiply to 1? Well, that will be 1 times 1, okay? But it could also be negative 1 times negative 1, okay? So it seems like I have two choices that will multiply to 1. But which one is the right one? I'm going to look at this number here. which happens to be 2. This is B, and this will be C, okay? A, in this case, is 1. Okay, A in this case is 1. But in any case, I'm looking at this B, here. And then I'm going to say, how in the world can I get a 2 out of this? Well, I could definitely get a 2 if we add 1 plus 1. Because if we add -1 with a -1, we'll get -2. So finding this set of numbers is critical in doing this thing called factoring. Okay. So what happens is that, I can then say that this expression, let me write it out, eraser, x squared plus 2x plus 1 can be written as x plus 1, and the other parentheses will be x plus 1 as well. So there it is. There is factoring. Okay. Of course, this would be like the simplest examples, but nothing wrong with starting simple and then making things a little bit more complicated. For example, this one, x squared plus 5x plus 6. I am very interested in the numbers that multiply to 6. That will be 1 times 6, or it could also be 2 times 3. And it could also be the negatives, right? It could also be the negatives. It could be -1 with -6, and it could also be -2 with -3. But I'm just going to leave my list like so. The question is, how do we get a 5? How do we get a 5? Well, if you're thinking about this, it could be 6 minus 1, right? But it could also be 2 plus 3. But there can only be one option. There cannot be 2. And one option doesn't work. And that will be this one. This doesn't work. Because if you multiply -1 times 6, then that gives you -6, which is a full contradiction of what you have here. So again, although 6 minus 1 is 5, when you multiply -1 times 6, that is -6, which contradicts the entire example. So therefore, this option is not it. It can only be the 2 and the 3. So therefore, in factor form, we have x plus 2, x plus 3. Simple, yes or no? Simple enough, right? Simple enough, okay? Let's not get too far ahead of the game. Let me do another 2 examples just to make sure that you and I are on the same page, okay? So we're still factoring. It's a very, very important skill. Expressions that look like so. Expressions that look like so. And I'm going to give you something like this. X squared minus 7x minus, let's say, 30. Let's say 30. So what happens here? What happens here? Again, we want to look at the very last number, which in this case will be C. Okay. And we want to say one numbers, and this is the way I do it. I say, forget about the negative for now. I promise you that will work out. Just kind of list the numbers that multiply to 30. And I will start with 1 times 30, 2 times 15, 3 and 10, 5 and 6, and that's about it. There's nothing else, okay? Not 7, no 8, no 9. 10 is already there, so we got everything. Again, trust me when I say the negative will fix itself. Just figure out what numbers multiply to 30. So then we say, okay, we got this list of numbers. The one that's going to tell us which one will actually work is this one right here. This is B. We need to figure out of these pairs of numbers, how can we get a -7? Let's put our heads together. How can we get a -7? Using these pairs of numbers. Using those two, using these two, or using those two. How can we get a -7? Well, I can tell you what. That's right. It's not going to happen with 1 and 30. It's not going to happen with 2 and 15 because the best you could do is 13. And you cannot do it with 5 and 6 because the best you could do is just 1. It's going to have to be 3 and 10. However, to get that -7, 10 must be negative. And if you triple check 3 times -10 is -30. So we're triple checking that things are working out. Okay. So now that we know these magic numbers, this is just x plus 3, x minus 10. Or if you want, you could do x minus 10, x plus 3. It doesn't matter what the order is. It doesn't matter. Are you with me or no? Okay, okay. All right. Well, let's see. Awesome. That's awesome. Let's see how we're going to use this in solving some equations. So let me go back to Alex now. Let me go back to Alex. Of course, it logged me out. Yeah, I don't even know if you're Alex then or no. All right. Well, thank you for being here. I appreciate you being here today. I know it's probably taking a little longer, but I really hope that this is helping you out. Okay, I need to log in. You log in and let's see we use this. So definitely the multiplying and dividing complex number that is showing up. Okay, that is showing up. So it will be part of the topics. But let me go ahead and look at how the factoring is going to come up in the what am I trying to say here in the solving of equations. Okay. Okay, let's see. Where is it? Okay. What is this? Oh, okay. That's interesting. Um, that's also interesting. So dividing complex numbers, where is it at? Where is it at? I'm looking for the thing and I can't find it. I want to show you what I'm looking at. So give me 1 second here. I want to show you what I'm looking at. So I'm trying to find the topics that include this factor in business, and I can't see it. Oh, okay. Solving an equation written in factor form. Is that it? Okay, I could do that. That's not going to take me too long. Okay, that's definitely not going to take me long at all. Where are the other ones? This one, okay, this one. Okay. All right. So here's what I'll do. I'm gonna do these, I'm gonna do, what happened? I'm gonna do this one, and I'm gonna do this one first. Okay, these type of examples first, and then I'll do the other ones. Okay, so let's go ahead and let's go back to the PowerPoint. And I think I need to share the PowerPoint too. Let's see, where is it at? Can you see the PowerPoint? No, okay. How to do this? How to do this? How to do this? Uh, it's here. I don't know. More sharing options. Okay. I'm trying to figure it out. Maybe it's up here somewhere. Oh no, it's gonna be up here. It's gonna be here. Okay. That's what it is. And so, how about this? I don't. Okay, let's do it again. Okay, we're gonna do this. We'll do that. Okay, so you can only do one at a time. Okay. And can we see the PowerPoint now? Yes. Okay. Awesome. All right. So let's go ahead and do some very simple examples first, and then we'll take it from there. So many little button things. Oh, kind of annoying. And then we'll do a couple of screens like so. Okay. Alrighty, then we're here. And let's solve these kind of examples that they had. Let's solve these kind of examples. They had it like, they look like, so it was solving equations. In factor form. And so they look like so. So some of them look like this. 2x plus 1, and then we have 3x minus, I'm going to say maybe minus 4 equals 0. The idea is this, okay? When you have a multiplication, remember, the parentheses imply multiplication. So when we have multiplication, A times B equals 0, the only way that this can be true is if and only if A is 0 or that B is equal to 0. That is the only way that we're going to be able to get a 0. For example, 0 times 7, that's 0. Or -5 times 0, that's 0. So that's what I'm trying to tell you here. And so when here we understand that there is a multiplication of two items that equals to 0, it can only mean that either this quantity here is equal to 0 or that this other quantity is equal to 0. Okay? Well, now we know how to solve these simple linear equations. So I'm going to do minus 1, minus 1. We have 2x is equal to -1. And then we divide by 2. X is equal to -1/2. Or it could be, that here we add 4. 3x is equal to 4. Divide by 3. X is equal to 4/3. So this particular equation has two solutions, and those are the numbers -1/2 and 4/3. Okay. Let me do another example that might be a little bit more complicated. Oh, my apologies. Let me give you some time there if you needed to see that or maybe take a picture, whatever the case might be. Okay, I'm going to move on. So let's say I was doing something a little bit more complex. 5x minus 15. And then I'm going to put here x. And then here I'm going to put 3x minus, I don't know, 21. I don't know. And that's equal to 0. Okay. So what I usually find is that students tend to forget. Students will do this. 5x minus 15 is equal to 0. It's very common for students to make like a little line there. And then they'll do 3x minus 21 equal to 0. But what happens is that they forgot the very first thing. That also needs to be set equal to 0. So x is equal to 0. Okay, so students forget that very first part. There's really nothing to solve here. This is already solved. The answer here is 0. But we got to do the other two, so we'll do the other two relatively quickly. So there I'm adding 15 on both sides. And so therefore I cross those out. 5x is equal to the number 15. Dividing by 5. Divided by 5. X is equal to 3. And then here we need to add 21. 3x is equal to 2. Oh, whoa, 21. 21. Dividing by 3. We get that x is equal to 7. So here we actually get 3 solutions. Don't forget the 0, the 3, and the 7. And it doesn't matter what order you write them, as long as you write them down. Okay, so wanted to show you that. So don't forget about these terms out front, which can be very easy to forget. It could be that maybe out front, instead of being x, it's 2x. Okay, divide by 2, x is still equal to 0. X is still equal to 0. Okay, that doesn't change. So just wanted to show you that. And so let's go ahead and do the example that they had. Oh, that's on that. Let's do something like this. Now solve the quadratic equation. And let's say we got something that looks like this. X squared plus 5x. And let's do here, let's do with, plus 4 is equal to 0. So the way to do this is that we need to take, for some reason I feel like using this marker here or whatever this is. I don't even know. I thought these were supposed to be pens, but I think they're all the same thing. I'm gonna use maybe this color purple. So what we're going to do is we're going to take this quadratic expression and we're going to write it in factor form. So we're going to factor this. We're going to factor that. And remember that the way I did this a little while ago is we were paying some very close attention to this number 4. Because we need to figure out what numbers multiply to 4. 1 times 4 and 2 times 2. So which one is the right combination? We look here. We look at B. So I'm just gonna write. We're looking at x squared plus bx plus c is equal to 0. So how do we get a 5? Hopefully you are able to identify this relatively quickly, that it must be 1 and 4. because 2 and 2 just not going to work out. So therefore, in factor form, this is x plus 1, x plus 4 equals 0. Using the skills that we just did a few minutes ago, this is the same as x plus 1 is equal to 0, or x plus 4 is equal to 0. Minus 1, x is equal to -1, minus 4, x is equal to -4. The solution set is these two numbers. How do you feel about something like that? And be honest. Okay, that's okay. I'm going to do easy. Oh, that's awesome. Not too complicated. That is great to hear. That is great to hear. That is awesome. I'm going to do one more example, and let's see if I can think of one that is a little bit more fun. Let's see. I'm thinking. Let's see if I can do so. X squared. Let's see if I can think of something fun here. Okay. -11x. I am going to do 24 is equal to 0. I'm going to let that be there for a moment. I'm going to let that be there for a moment so that you can look at it and maybe you're writing it down, okay? Maybe you're writing it down. Alrighty then, I think I'm going to get going here. So what we're going to do is we're going to factor this thing. This thing needs to be in factor form, okay? So if it needs to be in factor form, we need to look at this number here. And we need to list all the numbers. This is the way I do it. What are the numbers that multiply to 24? 1 times 24. 2 times 12. 3 times 8. And then 4 times 6. But I'm going to challenge you into, okay, now that we got the list, how can we get a -11? How can we get it? Oh, that's right. Good job. A -3 and a -8. If you look at all the other, good job. If you look at the other combinations, we're not going to get there. We're not going to get an 11. Okay. But let's triple check. If we multiply -3 with -8, what number do we get? Positive 24. So I'm triple checking that not only am I getting the right numbers that combine to -11, but I come back and check and make sure that that multiplies to 24. So therefore, in factor form, that is x minus 3, x minus 8 is equal to 0. From here, we use the same skills, the skills that says that if a times b equals 0, then that means that either a equals 0 or it means that b is equal to 0. So we are applying here. This is referred to as the zero factor property. That's the name of it. Okay. So here we apply the zero factor property, which says that either this is equal to 0 or that this is equal to 0. And therefore, well, hopefully from here, it shouldn't take that long to get the solutions. Bam, there it is. 3 and 8. Viene. Oh man, after I've done a couple of these examples, it feels like this is getting too easy. Okay. It's getting too easy. My apologies. I'm gonna come back to this. Okay. All right. I think I'm going to do one more topic. I think I saw one that kind of seemed a little different than the others, so I'm going to tackle that particular topic. Okay, so I'm just giving you a chance if you're writing this down, that you're writing it down. Okay. All right, so let me go ahead and let me go back over here and let me make sure that I get the topic that I want to look at. Where is that one? We did those. We did those. So that's plus to quadratic. Let's see. Oh, okay. Oh, wow. Okay. Let's see. Okay, this one right here. All right, so let me copy this down. So that would be 5. I just need to be able to write it down. So give me 1 second. So 5 over 4x plus 12 minus 3 is equal to negative 3 over x plus 3. All right. Whoa, that's okay. Okay. I'm going to, okay. Then 4x plus 12 minus 3 is equal to negative 3x plus 3. And we can go ahead and there's really no need for all of this. Or maybe there was. I don't know. I'm going to rewrite it again. I don't feel good about this. Oh, that's better. 4x plus 12 minus 3 is equal to negative 3 over x plus 3. That's awesome. So if you remember when I did this in class, I really paid attention or close attention to the denominators. Here, I feel like they're being a little bit tricky. Again, this is the denominator. This is also another denominator. But I feel like they're being tricky. Okay? And I'll tell you why. This denominator has very similar things as this one because it is 4x plus 3. If we look at it, if we pay close attention to this expression and we look at this term and we also look at that term, what I recognize about these two terms is that they are both divisible by 4. I can divide this by 4. I can also divide this by 4. So I can show that by taking a 4 out and then dividing by 4. That's why we get 1x, and that's why we get a 3. Okay? So what I notice is that, again, these two terms, as I looked at them and I paid close attention to them, what I did was that both of those terms are divisible, or they have a 4. We could probably say it like that too. They're both divisible by 4. So if we take out the 4, if we take out a 4, okay, like I did here, and I put it off to the side, 4 divided by 4, or 4x divided by 4 is 1x, and 12 divided by 4 is 3. All right. So now let me rewrite this. Let me go ahead and just kind of rewrite this as 4 times x plus 3 minus 3 is equal to negative 3 over x plus 3. Okay. Now remember that when I did this, I was paying attention to the denominators. So I'm noticing right now that a common denominator is going to have x plus 3. It's here and it's also here. So I don't need to write it 2 times. I just need it 1 time. Okay. But it looks like I'm going to need a little bit more than just x plus 3. We will also need a 4. Am I making sense? Yes or no? Okay. There's definitely no need to repeat the x plus 3's because it's already there. I see it. But one of the things is that we also notice that we need a 4 for the common denominator. Okay. So what I'm going to do is I'm going to multiply by this quantity 4 times x plus 3 times 5 over 4x plus 3 minus 4x plus 3 times 3, okay, times 3 is equal to, I guess I'll do it here like this, negative 3 over x plus 3 times 4x plus 3. And please let me know if this doesn't make any sense. Please let me know if this doesn't make any sense. I'm thinking we're good. I'm thinking we're good. All right, so what happens? The 4x plus 3 and the 4x plus 3, they just cancel each other out. Here we have, and be very careful, here we have a negative 4 times 3 will be negative 12 times x plus 3. Now, when we distribute, we get negative 12x and we get negative 36 equal to, on this side, the x plus 3's cancel and we get negative 12. So let me make some room so I can finish this out. So here, it seems like we can combine some like terms. So we get negative 12x minus 31 is equal to negative 12. Negative 36 plus 5 will be negative 31. Here, I will add 31. So the 31s will cancel. Negative 12x is equal to, what was it in this case? So 31 minus 12, we get what, 19? Okay. And then we'll go ahead and divide by negative 12. The negative 12s cancel out and we get negative 19 over 12. Questions? No questions? All right, let's do one more of these examples and hopefully we'll clean it up as we go through the next. So let me go ahead and copy it down because I didn't do such a hot job next time. So let me go ahead. I'll do this. I'll do this. And where did it go? Okay. Let's put it. Okay, let's see. All right, let me try another one. And I'm gonna write it down here on my paper and we'll work it out together. I'm just writing it out. All right, let's see. And this will be the last example for today. I don't want to overwhelm you with stuff. And hopefully the stuff that we did was pretty solid to kind of get very, very close to that 22. Yeah, this example, yes. In these type of topics, yes, the denominators will be, they're going to be so similar that it's even scary that they're so similar. Okay, check this one out. Here we have 2x plus 12 plus 3 is equal to negative 2 over x plus 6. So yes, you're right. I mean, the denominators are going to look so close to one another that is going to be even scary. Okay. So the one that I want to pay attention to right now is this one. Oh, well, that didn't work out. I don't know why it doesn't. Okay, that doesn't work. I'm curious. What does this look like? Oh, okay. I want to pay attention to that because something about 2x plus 12. I don't know. There's something about these numbers. What do you think? What do you think about these numbers? Something about these numbers that they have in common. 2 and 12. I wonder what they have in common. And the answer will be that that's right. That's right. They're both divisible by 2. I see you. So they're both divisible by 2. So let's put that 2 out and actually divide each one of these terms by 2. So if we divide this by 2, we'll get x. And if we divide 12 by 2, we'll get 6. So let me rewrite the example. And you're right, the x plus 6 is there. So let me rewrite this. This is negative 4 over 2x plus 6 plus 3 minus 2 over x plus 6. So now that I did that, the common denominator is going to be x plus 6, or is going to have an x plus 6. But what else is it going to have in addition to the x plus 6? What else? And you're looking at the denominators and you say, well, wait, there is a 2 there. That's right. Let's put that 2 there. So this is going to be the magic thing that is going to clear all the fractions. So yes, it takes time to write it down, but I'm going to write it down anyways. Times negative 4 over this. Here I'm going to say plus 2x plus 6 times 3. Okay, just be careful there. Here we have that, and then here I'm going to write 2. What am I saying? I am writing times 2 times x plus 6. And then we notice that this entire quantity gets canceled with that entire quantity, so we get negative 4. Here we get 2 times 3 is 6. And then we do distribution and we get 6x plus 36 is equal to, here we get x plus 6 is gone, and we get negative 4. Okay? What we notice on the left is that this negative 4 and this 36 combine to 32. So we get 6x plus 32 is equal to negative 4. Minus 32 6x is equal to negative 36. Dividing by 6, we get that x is equal to negative 6. There's the answer. Oh, there's something about this answer that I do not like. There's something about this answer that I do not like, and I'll tell you why. And let's see, let's find a red pen because we need a red pen now. Look at this right here, and just kind of look at this for a moment. If x is equal to negative 6, and then we add 6, that becomes 0. And I don't want to tell you the story right now, but dividing by 0 is a no-no. We are never allowed. This is definitely not, this is a no-no. So therefore, even though we did a whole lot of great mathematics and it looks awesome, this particular example has no solution. Because something, I don't know, I was like, oh, negative 6. And then I quickly looked over. I was like, oh, wait a minute. If x is equal to negative 6, it makes the denominator equal to 0. And that's a huge no-no. It cannot happen. It cannot happen. So this particular example, even though we did a whole lot of work, it has no solution. Okay. The other one had no issues. This, whatever answer we found here, what was the answer? This negative 19 over 12. If we look at this denominator here, it had no problems. No problems. This one, there was a problem there. I quickly checked. I was like, oh, hold up. That's a no-no. Cannot divide by 0. So unfortunately, after all that hard work, that example has no solution. Okay? Alrighty then. I'm going to leave it alone for now. That's as good as it's going to get for today. It's been already almost an hour and a half, so I'm going to stop this.